Hello. So last time we had seen about bounded, monotonic, and convergent sequences. We had seen about the definitions and we had also seen examples. Okay, but what if I give you a sequence and you need to check whether it is bounded, monotonic, or convergent? Okay, you may think that this is a very easy question. Okay, you can just uh, uh, you can just plot them out or just calculate them and then just conclude it from the picture. Okay, but that cannot be accepted as proof. Okay, we have to prove it. Okay, we will have to use either definitions or we will either have to use properties. Okay, but for now, since we only know definitions, okay, then we will have to resort to definitions. Okay, so that's why we will prove everything by using definitions for now. Okay, if there are properties, maybe we can use them later. If not, then we will always have to stick to the definitions to prove something. Okay, so we had seen that the definition of bounded sequence, this one. Okay, the question is this. Okay, prove that xn equal 1 by n is bounded. Okay, so over here we have, what exactly do we have to do if we have to show that it is bounded? We have to show that there exists k. In other words, we have to find k. Okay, we have to find k. K is a real number such that this happens. Okay, k, it can be very large or it can be very small, depends on your choice. Okay, how exactly do we find k? First, we need to calculate a few terms. Okay, 1. Okay, x1 is 1. If we expand it, we will be having this. x2 is 0.5. We had seen this sequence many times. Okay, 0.33. x4 equals 0.25. Okay, it continues in this way, or we can plot them in the number line. 0, 1 is over here. Okay, so the terms of the sequence are actually, they are present inside this wall. Okay, they can be in the wall, okay, but they can never cross this wall. So which number should we take? We should take this one. Okay, so k will be equal to 1. Okay, actually, how exactly do we settle the choice for k? Just take the modulus of 0. It will be 0 only. Just take the modulus of 1. It will be 1. Now choose which of these is greater. Okay, so the greater one is equal to 1. So that's why we will take k is equal to 1. Okay, proof. Take k equal to 1. Then modulus xn. Okay, 1, it is indeed a real number, so I'll just write it down. Modulus xn, it will be equal to 1 by n. Okay, now is this one less than k? Okay, 1 by n, is it less than k? Okay, so you may think, okay, I don't know. Okay, because n, it is a natural number. You may think that you don't know, and some of you, it may be clear, okay, that it is indeed less than 1. Okay, we have to show that modulus xn less than or equal to k. Okay, actually this line, it's not required. Okay, we can easily jump to this line. We have to show that xn less than or equal to k. How exactly do we show it? Okay, we will do something which is called as proof by contradiction. Okay, by contradiction. This proof works in this way. We have to prove something, assume the opposite. Assume the opposite, then get a contradiction. Assume the opposite. That is, assume xn greater than k. So if we assume xn greater than k, so we get modulus xn will be modulus 1 by n, which is greater than 1. Okay, we are assuming the opposite, so we are just following what our assumption gives. Modulus 1 by n, modulus of 1 it's 1, modulus of n, and it's also positive. Okay, because it is a natural number greater than 1. Okay, so 1, if you cross multiply, you will be greater than n. And n, it is a natural number, keep that in mind. Is this one possible, that 1 is greater than a natural number? Is it possible that 1 is greater than a natural number? It can be equal to 1, but it can never be greater. So that is why, okay, just to keep in mind, okay, so just to keep in mind, okay, n is a natural number, we have to prove this, but this one is impossible. So that is why we assume something the opposite, we get something that is impossible. So this one, it is a contradiction, hence assumption is wrong. If the opposite is wrong, so the statement now becomes true. Therefore, xn less than k. Okay, so this is a very powerful technique, okay, the proof by contradiction, which we will use many times, especially when dealing with inequalities. Okay, if we have no other way how to settle inequalities, this is one of the ways that you can do it, by using contradiction. Okay, so I hope you are clear. Let us take a look. Okay, maybe another example. Number 2, xn equal, okay, well, how about this? Okay, about 10 by n. Okay, this one, okay, maybe n plus 1 by n. Okay, let us make it a bit difficult. Okay, how about 3n plus 1 upon 3n. Okay, maybe just n. All right, let us keep it in this way. Okay, 3n plus 1 upon n. Okay, again, if we have to find k, we just have to look at a few terms. Okay, when we put n equal to 1, okay, we will be getting x1. x1 will be 3 into 1, so we will be getting 4. x2, you will see 3 into 2, 6. 6 plus 1 is 7, so 7 by 2. Okay, so now it has decreased. x3, 3 into 3, 9. 9 plus 1 is 10. 10 by 3. Okay, 3.33. x4, okay, 3 into 4, 12. 13 by 3. Okay, you can keep on doing it. Okay, you will see that the terms are decreasing. Okay, but they can never be negative. Okay, if they can never be negative, okay, because n is always a natural number which is positive, so n is also a natural number which is positive. So that's why the terms, they are between 0 and 4. Again, what we can do, we can take the modulus of 0, we can take the modulus of 4, which gives us 0 and 4. Okay, so what we can do now, we can take the greater of these, so take k equal 4. Okay, we need to prove xn less than k for all n belongs to n. So assume the opposite. Assume that xn is greater than k for some n belongs to n. Okay, so the opposite of less than or equal, it is greater, and for every, it is for some. Okay, the opposite of for every, it is for some. The opposite of less than, it is greater than. Okay, so this is what is happening. We have assumed the opposite. So if we assume the opposite, we will just follow with what we have assumed. So modulus 3n plus 1 upon n, it's greater than k, which is 4. 3n plus 1 upon n, it's greater than 4. Okay, we can take this one to that side. You will be getting 1 greater than n. Again, it is impossible. Okay, so if it is impossible, we are done. So therefore, our assumption is wrong. That is why xn is greater than k. Okay, so I hope that is clear how to prove about bounded sequences. Okay, actually over here we have said that we can take k equal to 4. Okay, so we have constructed a wall from over here. You can easily take k equal to 5 as well. There is no problem. Okay, if the wall, if a smaller wall works, then a bigger wall will also work. Okay, so keep that in mind. Okay, you can easily take k equal 5, k equal to 6. It is entirely on your choice. But again, I keep on repeating, why build a bigger wall if you can build a smaller one? Okay, so keep that in mind. There's no harm, but why do it? Okay, so that is how we prove about bounded sequence. Okay, now let us say, how do we prove monotonic? Okay, so that xn equal n is monotonic. Okay, so over here, we have to show that it is monotonic. It doesn't mention whether it is increasing or decreasing, but just by calculating a few terms, we are saying that it is indeed monotonic increasing. Okay, this can be seen as a proof, but again, we are going to use the definitions. Okay, so since it is monotonic increasing, so remember that xn plus 1 is greater than or equal to xn. Okay, for every n. Okay, this is the definition for monotonic increasing, or we can just subtract them and will be greater or equal to 0. Okay, so this is the basis for our proof. Okay, the definition was given in this way about monotonic increasing. So this is how we start the solution. Xn is equal to n. So how much will be xn plus 1? Okay, instead of n, I can write n plus 1. Now what do? We can just find out how much is xn plus 1 minus xn. It is n plus 1 minus xn is n. N plus 1 minus n will give you 1, which is indeed greater or equal to 0. Therefore, it is monotonic increasing. Okay, so this settles the first part of the this question. Okay, about monotonic increasing. It's very easy, and if you have to deal with strictly, then you should remove this sign. Okay, and for monotonic decreasing, you just calculate xn plus n minus xn. Again, you should be getting less than or equal to 0. Okay, but again, let us have a look at a different example. Okay, it's a sequence. xn equal n by n plus 1 monotonic. Again, we have no idea whether it is monotonic increasing or monotonic decreasing, and we don't even have an idea whether it's monotonic. Let us just calculate a few terms. Okay, so x1, it will be 1 by 2. Okay, if you substitute 1 over there. x2, it will be 2 upon 3. x3 will be 3 upon 4. Okay, if you calculate, this one will be 0.5. So this one will be 0.6. Okay, 6, 7. Okay, approximately, and 4 by 3 will be 0.7. Okay, so it looks like it is monotonic increasing. Okay, so okay, approximately. Okay, so solution, since we have to prove about monotonic, we have no other choice. We have to calculate xn plus 1 minus xn. So xn plus 1. Okay, instead of n, replace it with n plus 1. So you'll be having this. Instead of n, again replace it with n plus 1. But also you have this extra 1. So this is what we are having. Okay, so just replace n with n plus 1 over there. You will be having xn plus 1. xn will be as it is. So this one will be n plus 1, n plus 2. Okay, so this is what we are having. We can take the LCM. So this one will be n plus 1 whole thing square. Okay, do the LCM. So we'll be having this. So you can keep on calculating. Okay, a plus b whole thing square, n square minus 2n, n plus 1, n plus 2. Okay, so this is what we are having. N square 2n, n square 2n will get cancelled, so you will be having only this. Now you just need to check, is this term, is it greater than 0 or is it less than 0? Okay, you can easily tell, n it is natural number, so this one will be positive. N is also a natural number, so n plus 2 will also be positive, and this one is also positive. Okay, so positive divided by this, everything will be positive. That's why it will be greater or equal to 0. In fact, we can easily write it as greater than 0. Therefore, it is strictly monotonic increasing. Okay, again, if it is greater than 0, it will be monotonic increasing. Less than 0, monotonic decreasing. Okay, so this, okay, I hope you are clear with how to prove about bounded monotonic increasing. Now let us do some problems based on convergence. Okay, by using the definition, prove that xn equal 1 by n converges to 0. Okay, we already had a rough idea that it converges to 0, but okay, we need to prove it by using the definition using epsilon. Okay, just to remind you, xn converges to x if there exists n belongs to capital N, so that xn minus x less than epsilon for all n greater than n. Okay, so we'll have to use this definition. Okay, solution, we just have to be clear what is xn. And this one, it converges to x. Okay, so x is equal to 0. If for all epsilon greater than 0, okay, I mistakenly wrote the definition. So this is the correct definition. For all epsilon greater than 0, there exists this so that this happens. Okay, so what exactly do we have to do over here? You must remember that using epsilon and n, okay, or sometimes delta when doing above functions, you must know that epsilon is something that you can think that I am giving it to you. Okay, I give to you the value of epsilon. You need to find capital N. Again, I repeat, I give to you epsilon. You will have to find this capital N. Okay, let's see. Okay, so that's why we will start with what I give to you. So let epsilon be greater than 0. Okay, epsilon be greater than 0. Now you will have to produce this capital N. How exactly do you do that? It is by using this. Okay, now let us first calculate xn minus x. So it will be xn minus x, it will be 1 by n minus 0. So you will be having only 1 by n. Okay, what exactly do we want? Okay, this is not part of the proof. Okay, but we need to write it down as a kind of rough work. We want that 1 by n, okay, xn minus x less than epsilon. Okay, so that is 1 by n less than epsilon. Since you want to give me this capital N, what do I have to do? I will only have to keep only n on one side, transfer everything else to the other side. Okay, this can be done in this way, or we can write it in this way. 1 is greater than n epsilon. We can write it in this way. Okay, or we can write it, okay, 1 is smaller than n epsilon, so n epsilon is greater than 1. We will keep only n in one side, so we'll be having this again. Okay, this will be the basis for your reasoning. Okay, but you will have to write it down as a kind of rough work, so that you will clearly see how exactly we are getting this n. Over here, what we will write is this: less than epsilon whenever okay, we will write it in this way. So since we need to find this capital N, okay, taking n to be a natural number, okay, since it has to be a natural number such that n is greater than 1 by epsilon. Okay, we can always choose a natural number that is greater than 1 by epsilon. Okay, for example, if I give you epsilon equals 0.5, okay, 1 by epsilon, you can calculate it. Then you can give me a natural number that is greater than 1 by epsilon. Okay, you can always do that. Okay, so if you take that one, you can easily write it in this way. Then xn minus x, which is 1 by n, is greater than 1 by epsilon. How do I know that? It is from here. Okay, if n it's greater than 1 by epsilon, it's like reversing the steps. Then you will be having xn minus x, okay, sorry, it's less than epsilon for all n greater than capital N. Okay, so you can easily write it in this way. Okay, so this completes the proof. We had find capital N which depends on 1 by epsilon. Okay, so this completes the proof. Okay, another question that I will be doing. Okay, 1 by 2 power n converges. If you put n equal to infinity, okay, you can think of it in this way: 1 by 2 power infinity. It will be very, very small. That is, it will converge to 0. Okay, 1 divided by a very large number will be converging to 0, almost equal to 0. Okay, so again, over here it is the same thing. So xn equal 1 by 2 power n, we need to be clear, and x is equal to 0. So let epsilon be greater than 0. I give this epsilon to you, which is a positive real number. Now xn minus x, calculate it. You will be having 1 by 2 power n minus 0. You'll be having 1 by 2 power n. Now comes the rough work. Xn minus x less than epsilon. Xn minus x we had calculated. We had gotten 1 by 2 power n. We need to isolate n. Okay, we need to keep only n on one side. So you'll be having 1 less than 2 power n epsilon. Or we can easily write it in this way. Since we need to isolate it, okay, if you are comfortable, you can easily jump from this step to this step also. That is acceptable. Now, how do we isolate this n? Okay, it is by taking logarithms. Okay, and if you remember that logarithmic function is monotonic. Okay, that is why we can do it. Okay, if this is greater than this, then because it is monotonic, then we can easily write down that log will be greater. Okay, this is very crucial. Okay, sometimes you may be thinking, why are we studying about monotonic functions? Why do we need to say that logarithmic is monotonic? Okay, so this is the point where we are using that. Okay, logarithmic function is monotonic. Okay, so log 2 power n will be n log 2. Okay, we can keep the answer, we can keep it in this way. It is acceptable. Okay, so taking, or if you want, you can simplify, your choice, taking n to be a natural number, such that capital N greater than log 1 by epsilon by log 2, we get xn minus x less than epsilon for all n greater than n. Okay, so this completes the proof. Until next time.